In this lecture, I want to talk about the power dissipation in a basic NMOS inverter. And we're going to take a pretty simplistic view on this, but it will give us nevertheless a chance to just think about power dissipation in circuits and in switching circuits in this case. Up to this point, we've looked at, the logic inverter more from its functional perspective. It's a logic inverter, or maybe it's even an amplifier, but we've not considered power that might be dissipated in it. So that's what we're going to look at right now. So our model is going to be really simple. We're going to treat as an SR model. Okay, so either it's going to be an open switch or it's going to be a closed switch with some RDS on. Okay, this is a very simple model, but it'll suffice for what we're wanting to do. So this is when VGS is less than V threshold. This is when VGS is greater than V threshold. And at this point, you know enough about MOSFETs to know that fully closed state does not occur just the nanovolt past the threshold. You have to go some distance beyond that. But we're going to drive this thing with the square wave. So we'll say Vn here is a square wave going from 0 to 5 volts, and it has a it has a period of capital T, and it has a pulse of D times capital T. Okay, where D is the duty cycle. So D ranges between 0 and 100%. So if the duty cycle is 50%, if it's a square wave, then the duty cycle would be 50%, and we'd have half of our period up at 5 volts and half the period down at 0 volts. Okay, so we're going to drive our inverter or our MOSFET with this square wave. So what we'll get at the output is going to be the inverted version of that. So we have two circuit modes that we have to look at. Two circuit modes. All right, one is going to be when Vn is equal to 0, or I should say less than V threshold. All right, we're going to have VDD, and then our switch will be open. Okay. Now we haven't connected anything to here, but if we were to connect something, okay, let's say that we actually connected something, a load here. I call this RL. Okay. So what we'd have here is RL connected to VDD through R1. And that's basically our circuit. Now if Vn is greater than V threshold, then we're going to have VDD shorted through R1 and through the MOSFET. Right? Oh, sorry, I should have RDS. I have RDS on at that point. And we'd have RL as well in parallel with that. Okay? So let's consider what kind of power we have dissipated in both these cases. Now, in the first mode, we'll call it circuit mode 1. We'll call this circuit mode 2. Okay? This is going to last for, let's see, well, we'll say the first one is going to last for 0 to D times T. Right, so a duration of D times T times the period T, and this one is going to last from D times TS to TS. So it has a duration of actually 1 minus D times T. Okay, so we'll keep that in mind. Okay. So the power dissipated is going to be equal to, power dissipated in the total circuit, okay, between R1 and RL in this case, is going to be equal to the total voltage VDD, V squared over R is basically what we're looking at, right? V squared over R1 plus R load. Okay, so that's the power dissipated during the time that we're in that mode. And so we'll hold on to that, and then we'll come back and use that in our final expression. Power, I'll call it PD1. PD2 for circuit mode 2 here is going to be equal to VDD squared over R1 plus RDS on in parallel with RL. But we're going to assume that RL is much, much greater than RDS on. Okay, that's a reasonable assumption. So therefore we can say that PD2 is approximately equal to VDD squared over R1 plus RDS on. Okay, so the average power dissipation is going to be equal to, so this is the average, total average power, will be equal to P, okay, I guess we'll do big P, PD1 times the percentage of time that we're in circuit mode 1, right? And we're in circuit mode 1 for the time 1 minus D times T, all right? And we're in circuit mode 2 for a duration of D times T. Okay, so this is when the switch is on, and this is when the switch is off. Okay, so we can rewrite this. We have oh, and I forgot. This whole thing is going to be times or divided by our total period, right? We're taking the average. So all our capital T's drop out. So what we end up with is PD1 times 1 minus D plus PD2 times D. So now let's try an example here. Let's suppose that we have VDD is equal to 5 volts. We have R1 is equal to 10 kilo ohms. We have RDS on is equal to 100 ohms. And we'll say RL is equal to 50 kilo ohms. Or maybe let's say 100 kilo ohms just to make this easier. Okay, so our PD1, let me rewrite this total power dissipation. It's going to be VDD squared over R1 plus RL times 1 minus D plus VDD squared over R1 plus RDS on times 1 minus D. Okay, or times D, I'm sorry. Times D. So, and I said, let's suppose duty cycle is equal to 50%. Okay, so we'll have power dissipation is going to be equal to 5 volts squared over 10K R1 plus R2, that's 10K R plus RL, 10K plus 100 ohms, so it's going to be 10.1 kilo ohms. Okay, times the duty cycle of 50%, because it's 1 minus 50%, plus 5 volts squared over R1 is 10K plus RDS on is, did I mess it up? I'm sorry. In the other case here, this is the one that's 10.1 kilo ohms. But in the first case, we have R1 plus RL, so that's 10K plus 100K. That's 110 kilo ohms. Okay. So what do we have? We have about 25 over 110 kilo ohms times 50% plus 25 over about 10.1 kilo ohms times 50%. And let's see, that amounts to 25, it would be 25 milliwatts, or 20, this is about 0.23 milliwatts, still times 50%, so it's going to be divided by 2, plus 25 over 10.1 kiloohms, which is about 2.48 milliwatts divided by 2. So it ends up getting us 2.71, so that'd be about 1.35 milliwatts. Okay, so that's the amount of power that is dissipated. Now notice that if you change the duty cycle and you spent more time with the switch on, we would actually have our power dissipation go up some more, because when the switch is on, we're applying the 5 volts almost entirely across R1, whereas when the switch is off, we're applying the 5 volts across R1 plus RL, which is a much larger resistance and therefore less current and less power dissipated. Now this here is called the static loss. Static loss here. Alright, same with, we'd call this here the static loss. So it doesn't matter in this case how quickly you're switching your transistor on and off. All that matters is the duty cycle, what percentage of the time you spend with your transistor on, and what percentage of time you spend with the transistor off. Okay, so we call that static loss. There's also dynamic loss, which is going to be a function now more of actually the switching. So let me just give you a quick preview on that, and then we really want to talk about capacitors a little bit more before we probably should talk about this, but I'm going to go ahead and give you a feel for it. So I mentioned in a previous video that there is parasitic capacitance, so between the different pins on a MOSFET. So let's consider V, or capacitance between gate to source. Okay, how does that affect things? So if I have my transistor and I have a capacitance hanging between here and source, which is ground, all right, and now I'm going to be charging Vn up and down from 0 to 5 volts. Now I didn't put a resistor in here, but if I put a small resistance, it'll become more evident. It doesn't change the result, but if I call this Rg, okay, what actually is happening is if you put Vn like this, we'll see that the voltage at the gate, Vg, will actually rise exponentially. Now that might be really fast depending on the values of Rg and the capacitance. But the thing that we want to highlight is note the energy stored. Stored in CGS. Right? It's going to be power in the cap in CGS is going to be equal to 1/2 CB squared. Okay, where the voltage will be the 5 volt, the 5 volts. All right, so we have 1/2 CGS VGS squared. So if, for instance, CGS was equal to, well, I'll just pick a big number in this case, but let's say 1 nanofarad. Okay, then P, the energy stored in the cap, would be equal to, at 5 volts, would be 1/2 10 to the minus 9 times 5 volts squared. 12.25 nanojoules. Okay, so what happens is every time you turn on the gate, charge the gate up, you're actually storing that kind of energy in the capacitor, and every time you turn the gate off, you're discharging that energy. And although we're not going to show it here, it turns out that you will actually dissipate the same amount of energy as you store. You will dissipate the same amount of energy in the gate resistance as the energy that you store in the capacitor. So we can say that a power dissipation, an active power dissipation, so I'll call it dA, is equal to 1/2 CGS times V, we'll say VGS high. Okay, so all that means is it's going to be squared. That's just the 5 volts, right? Okay, so 1/2 CGS VGS high squared, that's the energy stored in the capacitor. And every time you charge that capacitor, you're going to actually put that amount of energy in the capacitor, but in the process you will actually store or dissipate that same amount of capacitance in the resistance. Okay, so I don't expect you to necessarily follow that or know that, but that's the case. So when you charge the capacitor, you're going to burn as much energy in that gate resistance as you store in the gate capacitance, and then of course when Vn goes to 0, you're going to discharge the gate through that resistance, and so the 1/2 CV squared that you've stored will be dissipated. So actually we end up with this expression times 2. So we have just CGS times VGS high squared. Okay, so let's say that you had 1 nano. Oh, and I missed something here. Sorry, I'm sleepy. So you have 2 times, this is energy at this point, 1/2 CV squared is energy. You have twice of that, and then you're going to be doing this every switching period. So every T, capital T seconds. So you'll be doing this at 1/capital T frequency. So we can write this as times F, where F is equal to 1/T, the period of your pulse. Okay, so we have CGS times VGS high squared times the frequency. So what does that mean? We have, let's say we're using the 1 nanofarad, so 10 to the minus 9. We go up to 5 volts, so it'll be 5 volts squared, 25. And then let's say our frequency is, we'll just make it slow for this, 100 megahertz. Okay, so what does that end up being? So we saw before that was 25 nanojoules, but then this is times 10 to the 100 times 10 to the 6, that's 10 to the 8, right? This is 10 to the minus 9. So we end up with 2.5 watts. Okay, 2.5 watts of energy that is dissipated in that gate resistance in charging and discharging the capacitance. Now, this is absurdly high, but it just goes to show that even a small amount of energy stored, if you're going to be storing it and dissipating it quickly, often enough, it can amount to some significant power. So this is called the active power, or dynamic power, I'm sorry. Dynamic power dissipation. Okay, so it really takes the sum of the two, the static loss. So you go up together here and you say P total is going to be equal to the static loss plus the dynamic loss. Okay, and now you can see that the total power dissipation in a gate is a function not only of things like the voltage level of your logic, but also dependent on how fast your signals, your logic signals are switching. So as you go to higher and higher switching frequencies, clock frequencies on your processor, then you will have more and more frequent charging and discharging of all these parasitic capacitances, and that will lead to higher and higher power dissipations. And so that's the battle that's always being fought, to try to make things go faster you want to shrink them in size. You can reduce the energy stored in the parasitic capacitance, one, by either reducing that parasitic capacitance by designing smaller transistors, smaller feature sizes, or two, you can reduce the operating voltage, right? So instead of charging it to 5 volts, you can charge it to 3 volts maybe, if that's still enough to turn on the transistor. So these are just some things you can be thinking about when you think in the context of, what limits a processor from clocking faster than it does. And at some level, it really involves things like we're talking about here, where essentially clocking it faster will dissipate more energy internally in the IC because of charging and discharging capacitors, and that in turn could become a failure mechanism because of over stress thermally. So anyway, that's a little more information on calculating basic static and dynamic power dissipation for an NMOS inverter. There are obviously a lot of other details that can be provided. There are other capacitance in the circuits, and there are other sources of losses, but I wanted to at least just give an example of a component for each of the static and dynamic loss, so you can see how the static does not depend on frequency, but the dynamic dissipation does depend on the operating frequency of the circuit.